Previously, we learned about completely or fully reversed fatigue, the case where mean stress is zero, where we're going through equal parts tension and compression through our fatigue cycle. In reality, most structures are actually subject to more complex fatigue loading conditions, condition where we are not fully reversed and where there is a non-zero mean stress. So let's look at how we properly draw a stress time diagram for a typical fatigue test. In a typical test, mean stress is non-zero. It could be a positive value or it could be a negative value. In our stress time diagram, we'll typically, draw some kind of sinusoidal wave, and then the dimensions in this diagram are related to different values. The highest value on our stress time diagram is our maximum stress of our cycle. Our lowest value in the diagram is our minimum stress of a cycle, per cycle. The range, which is the difference between the max minus the min, is the total range of stress within our cycle. And if we take half of that range, we find our stress amplitude, which is the parameter that we use to assess against the cycles to failure. So the SN, the S is that amplitude. Then our final stress value to be concerned with is the mean stress, which is actually the average stress from our zero line to the average value of our curve, right? Now, mathematically, these can be expressed pretty simply, where the stress range is max minus min. The stress amplitude is the range divided by 2. So the max minus the magnitude of the max minus the min divided by 2. The mean stress is the max plus the min divided by 2. And so we've got our stresses pretty much laid out. Now, there's some other characteristics on this test stress time diagram that we also need to know if we're drawing one of these diagrams. One of them is the period of a cycle, which is the duration of a single cycle during fatigue. That is located once we've passed through our initial point 3 times. That represents a single cycle. If we were under fully reversed conditions, that would be passing through 0. But under a general state of stress, it's passing through our mean value 3 times. The time span that takes is called the period, tau, and it's measured in seconds, right? Another important parameter that we need to note, and that would go into our legend for this diagram, is the frequency. What is the frequency of cycling? And that is 1 divided by the period, measured in hertz. Let's actually go down to it. So the period is in seconds, frequency is in hertz, and there is this relationship between them, where period is equal to 1 over frequency, and frequency is equal to 1 over seconds, where hertz is equal to 1 over seconds. So you can literally just divide them by each other, and they're in the perfect units, right? Now, the last 2 parameters we need to put on this diagram are the stress ratio R and the amplitude ratio A. And these help us to understand the relationships, the ratios between the maximum and minimum stress and the stress amplitudes and ranges within our problem. Let's start with the stress ratio. So the stress ratio, R, is equal to the minimum stress divided by the maximum stress. So if we had a fully reversed case, then R would be equal to -1, because the min and the max are equal to each other but have opposite signs, right? One's in compression, the other's in tension. The stress amplitude A, that parameter relates the stress amplitude with the mean stress of our geometry. And of these two parameters, the most typical that you see in literature or you'd see on a stress life plot is going to be that stress ratio. That is the kind of the conventional thing that we would see in a legend. So now, hey, we've got the basic stress time diagram down. We know how to draw it. We know what all of the aspects in it mean. Now let's move on to the way that those wave functions might look. Now, sinusoidal waveforms are the most common. Those are the waveforms that we would, if we were doing an experiment, we would most like to use because those kind of smooth waveforms allow us to cycle very, very fast if we're doing an experiment. But many other waveforms could be applied to a material during an experiment or observed during actual operation, actual service of a structure. So we could have sine waves, we could have triangular waves, square waves, or even these top hat waves that kind of have a ramp and then a hat and then a ramp down, right? And of course, beyond these few, there are many other types of waveforms that are possible. Now, when we leave the laboratory and enter into the real world, we see some really interesting behaviors. In the real world, of a part subject to fatigue cycling, we have the potential to see high frequency ripples where there may be a waveform, but there's also micro fluctuations and vibrations that appear within the signal of stress over time. We also can have components that aren't perfectly operating on a nice sine wave. They can have skips or dynamicism in how long a period is. So periods can change, the duration of a cycle can change. And then in many operations, especially when the environment's at play, you can have non-sinusoidal and variable amplitude loading, where you've got kind of loading all over the place. You could be loading in compression a few cycles, loading in tension a few, fully reversed in a few, high frequency fluctuations in another set. All of that can be happening in an actual part under service. Now in the laboratory, we generally work in a much simpler place. We, of course, have our completely reversed, the Euler experiment. We could have pulsating tension. We could have positive mean stress. We could even have pulsating compression. We could even be cycling in compression and looking at certain perpendicular cracks in a structure, right? So now let's do a thought exercise. And let's ask ourselves just a basic question. If we think about stress over time and what's happening in a structure, given the two stress time diagrams below, diagram A and B, which test do you believe will fail earlier, fail sooner? Now in condition A, we've got a fully reversed condition. So we're going into tension and then equal parts compression and then back into tension. So we're going to tension and then into compression. In case B, we're going up to our mean stress. So we're opening up to our mean stress, and then we're opening more, and then we're unopening a little bit, but where a crack is still remaining open. And then we're repeating this with a very open crack over and over again. Which one fails sooner? Well, if we can think about case B where the crack is just permanently open and never has a chance to close, then that means that the driving force for crack growth and fracture is much higher under this pulsating tension case, right? Okay. Now let's move to another case. Let's do this again. Let's look at the two cases here below, and let's ask ourselves, which of these cases, case A, which is fully reversed, or case B, which is pulsating compression, will fail first? It's going to reach its cycle to failure sooner. Now, let's look at the case of case B. In case B, we have a crack, and then we go to a negative mean stress, so the crack stays closed, and then we unload compression a little bit, the crack stays closed, and then we increase compression a little bit, the crack stays closed, and repeat that ad nauseum. Under this case, we have very little driving force for a crack to grow. And so between case A and B, case A is going to reach its cycles to failure sooner. Overall, what we can say is that tensile stresses open the crack, allowing for more crack growth and earlier fatigue failure, while compressive stresses close the crack and typically do not contribute to crack growth.